Said I just so enjoy writing stuff. Okay, we are going to do a lab today.
Oh my God.
Ohm's Law Lab. It's a very quick and easy lab to make measurements on, provided you pay attention. List of materials has one of these in it. This is called a power supply. I want to talk about some of the ways that you hook stuff up and the different parts of this, but the lab itself is actually quite easy, and it's a good place to start working on electricity, so we're going to go from there. So first off, each group will need one of these power supplies. This is basically an adjustable battery, essentially. The knob, make sure you turn it to 0 when you start hooking stuff up, but otherwise it's very simple.
What, turn it to 100?
We are going to use the ports over here throughout our work. This is DC, and over here is AC. And yes, AC-DC was named after something like this. A sewing machine, actually.
Yeah, that's what I thought.
There was, near the plug on their sewing machine, it said AC-DC, indicating that you could plug this into an alternating current receptacle like we have in the walls, or a direct current source, and still run it. And that's where they got their name.
What if they named themselves DCAC?
Well, that would be strange. Nobody says that. Yeah, no, it just doesn't work. It'd be like, and then everything would be backwards. They'd be back in white, and I don't know. It wouldn't work. Just think about that. Think about the lyrics. It wouldn't work anymore. That's disturbing. I don't know where you're going with that, but stop. Now, so some basic terminology to go through. An electric current can be either DC, which is direct current, which means one direction, only one direction, also not a band, or AC, alternating current, in which the electrons move back and forth repeatedly. So we do, most of our electronics use DC. Batteries are good supplies of DC. However, it's much more efficient to transfer energy using alternating current. So when we generate, let's see, electricity generation and distribution and things like that, we use alternating current. Things that spin and create energy are going to create alternating current because of the nature of that being cyclical, going back and forth. And in next chapter, we'll talk more about electricity generation because it involves magnetism, and that's what we're studying next time. But just the nature of how that's done. If something's moving, which is almost all of our energy creation or electricity generation, it's going to be alternating current. And that's also a lot more efficient to transfer to homes. And even the outlets then are alternating current. But almost everything we plug into them nowadays actually requires direct current. So that's where you get those little boxes, your chargers. They're also called power bricks. They convert from alternating current to direct current. So computers, phones, TVs, all of those things have those power supplies, computers. All of those use it. There's one in here as well, which takes the wall outlet and converts it. Now, this has 2 ports. It can produce varying voltage here, alternating current. We really don't use this setting though. we use the direct current. We're going to use this stuff and a couple more things to create a very, very simple circuit today. This circuit starts with our power supply, and I'm going to show you the symbols that you'll see in circuitry diagrams for all of this because it's a way easier to draw. So we've got our DC power supply here, DC source. We've used this for batteries or like this thing. This line should be down just a little bit. I'll make sure to connect it better here. Well, that's no better.
Can you draw this in the circuit diagram part?
Probably once we're done, yes. And you don't need all the labels. You might want to put this labeled somewhere though. I still did it. That should just be down on that line. So there's our DC source. Whenever we draw a circuit, we're going to try and do right angles, straight lines, that sort of thing, because it makes it a lot easier to follow and a lot neater. I'll just draw the basic circuit. Then on the other side of the circuit, we're going to put one of these things, which is a resistor. In a circuit diagram, we would label that resistor with the amount it is. And I'll label just a generic one here, and we'll explain what it means down below. So maybe that's 25, and then the units are ohms, which are abbreviated there. Yours in the actual circuit diagram will vary depending on what you choose. This is a simple circuit. It allows electrons to flow from this side of the battery or source around. This is a negative side, and this is the positive side of a DC source. And I always remember that because that looks a lot more like a little dash, which is a negative. So technically, electrons are flowing out of this source of electrons and around, in this case, counterclockwise. Historically, though, when scientists first started experimenting with electricity, they didn't know what was moving. They could tell that it was some charge, but they didn't know the structure of the atom yet. So they actually said the current is flowing the other direction from the positive side around. We still do that today. It's just a historical thing that we treat everything as though it were a positive current flowing one direction, when in fact it's almost always a negative current flowing in the opposite direction, but everything works out perfectly because the directions are opposite, but so are the signs. So it doesn't end up mattering. We label this current, of course, with a capital I. I don't know why I. I'm not sure, but it is. Resistance gets a capital R. And then the last thing, this DC source, we measure the power of that in voltage, which we talked about yesterday a little bit, and that's V. So two of these make sense. Okay, and I'm going to summarize each of these down below. V is our voltage measured in volts. I is our electrical current in amps or amperes, which we abbreviate with a capital A. What is that? What do you think? Right. Yeah, if you had ninth grade, then this you've seen before. And we can't abbreviate ohms with an O because it looks too much like a zero. So we stole omega from the Greek alphabet. Now, I capitalized all of these, and all of, even that's the capital omega. Why do you figure they're capitalized? Named after people. Volta, Ampere, they were both Italians, and Georg Ohm was actually a German physics teacher doing all of these. We also discussed a little bit yesterday the relationship between volts and other units that we have seen. 1 volt is equal to 1 joule per coulomb, so energy over the amount of charge. We've got a similar measurement for current. An amp is equal to 1 coulomb per second passing a spot. I am not familiar with any such relationship with ohms. I mean, we could figure it out, but those two are the main ones. Okay, so we're going to be measuring 2 of these things. We'll be using resistors for this lab. I've got a couple boxes of them over here. I'd suggest using the larger ones only because they won't heat up very quickly. So this is one example. This one is actually, ironically, used in order to heat things, but not with the amount of current or the amount of time that we'll be using it for. It's very big so that any heat that's building up will spread out throughout it and be given off little by little. Every resistor has its value recorded on it. Every resistor you can actually hold and potentially read. So this one's actually just typed. It says 12 ohms right on it. Other ones, they come in a lot smaller sizes. So here's another one. Still large by most of today's standards. There's no text on this, but there's a color-coded ring. So this looks like a brown, green, red, gold. That's a code for the value of what's on there. The gold, I remember, means that it's very high precision. I want to say it could be a 1%, but it might be 5. I don't remember what the other ones mean, but I can guess now because the brown is probably a 1, the green is 5, and the red is 3. That third one is the place of tens. So this would be 1.5 times 10 to the 3. Right. No, 4. Red would be 4. I never bothered to learn those because we can also just measure it, or if I'm in a real pinch, I could look it up. But the rings are color-coded, and so people who have done it a lot can just look at a resistor and know how much it is. They come in smaller sizes. Those are also resistors. Smaller size does not necessarily mean lower resistance, though. It all depends on how easy is it for electrons to flow through this, which is a measure of resistance. And they come in still smaller sizes. So if you look in any modern electronics, you're not going to see too many resistors like this. We see other components, largish components that are called capacitors that we won't really deal with. But a lot of the resistors are these tiny, tiny things right over there. This size is called 402, I think 4 millimeters by 2 millimeters. There are 201s, so a quarter of the size of this, 2 millimeters by 1 millimeter across. And they're very useful for populating on boards like this because they're all done by machine or an unlucky electrical engineer who has to remove a whole bunch and replace a whole bunch of them just to test out what his board is going to be doing. You end up using 2 soldering irons, pinching them in between the soldering irons to heat both sides at once and looking at it through microscopes to be able to place your components. It's not actually as hard as I'm making it sound. It's okay. Okay, so that's our resistance. You'll pick one for the first measurement, and you'll hook it up to each side to one port of this using alligator clips. So named because nom nom nom.
Is that the real name?
These are alligator clips. I did not make that up myself. These are alligator clips. These one out are very common too. They get plugged into ports. These, of course, are called banana plugs.
Name these things.
Electrical engineers. Nom nom nom. So your basic circuit here, these ports are designed essentially to accept a banana plug. They don't do it very well. They're too loose. I don't know if that's just the general size of them has shrunk or over the years, or if there were some other cords. You can unscrew them some, and that shows a metal post coming out, and there's even a hole through the metal post, so you could put a wire through that, or a spade bit, which is sort of a C that goes in, and then tighten them down. That works too. But easiest way for us is just to grab one of these alligator clips, make sure they're screwed all the way in, and just clip inside it like so. Because that's going to make good contact. And it's very quick and easy to do. So we're going to make our first circuit here by grabbing a couple of the alligator clips. The thicker wired ones are nice because they are thicker wires. They heat up less, they have less resistance internal to them. And then we're going to take our resistor and put it across these two. And this is what I have drawn in the diagram up behind. Right? So it's our source, a pair of wires, which are just the straight parts here, and the resistor. Now we also want to make a couple measurements as part of our lab. One, we want to measure voltage across the resistor, which is a measure of how much energy, how many joules per coulomb, is being lost by electrons traveling through this. The way we draw that, I'm going to get rid of our resistor here, is we're going to clip in on both sides, so we just draw it out like so. A voltmeter to measure voltage is a circle with a V in it. I know, mind blown. Whenever we call this measuring the voltage drop, which means how much energy is lost through this, or voltage between 2 points, voltage is always measured from one point to another. It's a comparison. It's a potential energy. So just like when we have something at 2 meters up, we have to say, well, 2 meters up from what? Same thing with this. That will measure the voltage. We'll just leave this plugged in, and I'll show you how to set up our multimeters in a moment to do that. And then we also want to measure current, which is how many electrons are flowing through the circuit. Now in this circuit, an electron leaving here has to go through the whole thing in order to get back to the positive side, and that's its goal. So we can actually put our measurement anywhere in here and get the same value. Electrons won't really flow through a voltage meter. We'll discuss more why in a few days, but this is a very high resistance thing, so electrons don't want to go through it. It's only measuring side to side. A current meter, though, has to work sort of like a wire with a counter in it. So the way we're going to hook it up is to take out one of our wires there and replace it with wires going to our ammeter, which is the device used to measure current, or amps, and a voltmeter. Okay, so let's discuss what to do with that. I will leave these set up here so you can see how to do it, but I want to walk you through multimeters because they are just dead useful things. I use these around the house occasionally, not like every day, but good days. They measure lots of different things, hence the name multimeter. The first thing you got to know is whenever you're going to make a measurement, you put 2 wires into it. One always goes into this common port. Actually, maybe I'll pass these out so you can follow along. The COM port there means common. So one wire always goes into a common port. This will be our amp meter and our voltmeter, but you'll need 2 of them for lab. We'll just do one. Yeah, we don't want to use that. That is really obnoxious. Yeah, that's not much less so. So the first thing you got to know, one wire always goes into the common port for any measurement you're making. The other wire goes into the port depending on what you're measuring. So right above that, you'll see units. On the left, we have amps, then milliamps, and then on the right, volts and ohms. For our purposes then, we're going to grab a pair of wires for this. Electrons don't care which color the wires are, so don't worry about that. And since the first one I'm going to show you is voltmeter, I want to choose the common and the voltage one. Then we'll set the dial. The dial gets set based on what measurement you're making too. And you'll notice though that we have two V's over on the right. One with a pair of straight lines and one with a squiggly line. The straight line means direct current. The squiggly line means alternating current, because if you looked at the voltage, it's actually a sine wave. So we're setting up into the direct current. You always want to set into the lowest possible setting that still gives you a measurement. So the numbers here show you the maximum value that can be measured at that setting. So it goes from 200 M, so the max it could measure 200 millivolts, up to 2 volts to 20 and so forth. I think we're going to need a 20 volt setting for this because we're going from about 1.5 up to about 9. Okay, and then we're ready to just turn it on and clip it onto the two sides of the resistor with the alligator clips. That will just continuously then measure the voltage. When we turn up our dial, go by about, I think it says 1.5 volt steps, thereabouts. We also want to measure the current using an ammeter. So I only have this one left, so I'll have to take it off. There are 2 ports for current. Most of these, though, have, you notice that it says 200 milliamp max fused between the common and the first and the middle, the MA. There's a small fuse inside here that gets blown if a student, say, hooks it up and puts too much current through. The ones with the little sticker that have MA on them are the only ones that still have that fuse intact. For a while I was replacing them, and then I just got tired of it and stopped. That will still work fine for us. If you happen to have an MA on there, you certainly can use the milliamp port. Just keep in mind that if you're approaching 200 milliamps, you need to swap it out. For the rest of us, we're going to use the far left port for amps. That means that we need to, and you'll notice amps are measured on the left, we'll need to set it all the way over to 20 amps for that one to work. So it'll be a maximum of 20 amps, which will be more than enough, and then we'll get our measurements there. Now, the straight one, sorry, DC, yep, still DC because the squiggle still means alternating current. And then, as indicated by our diagram, this actually takes the place of one of our wires. Yeah, Kyra?
How are you supposed to know like what's going to be too much?
Well, usually with something like this, if you think it might be too much, you would not put it on that fused one. But for a voltage, it's actually okay. If it ends up being more than the scale can handle, it just displays a 1 point and then nothing else. And that means it's beyond the maximum of that scale, so you just turn it up to the next one. The only one that can be damaged at all is that fuse, if you're in there. Otherwise, it's perfectly okay. This one actually takes the place of one of the wires. So the electrons flow through it as though it were a wire and get counted. So I'm going to disconnect one of my alligator clips and put these two in their place. So one to the supply, the other to the other side of my resistor, and then as this goes up, it'll just report the current here. So if I have two, I could just leave them clipped on the two sides of the resistor and going from the power supply to the resistor, either side doesn't matter, and do that. And then the experiment is first experiment is just to increase the voltage, which you can read on your voltmeter, from I think 1.5 up to 9. Measure and keep the same resistance in each time, record voltage and current. Second one is pick one, and I forget what it says, but try only replace the resistor value then. So you'll pick different ones. I suggest the gold ones are nice. There's a variety of them. The gray ones are okay, but don't pick the ones on the upper side that say 1 ohm. That's going to heat up really fast and put these under too much stress. So stay away from 1 ohm, but you can certainly choose the rest. If you want a different variety, the little ones in here are good too. Don't go too high, probably no more than 200 or 300 ohms from in that first one, and just make sure they get back into their correctly color-coded bins when you're done. But these are also okay. Right. So I realize this will take you a little while as you're sorting things out. We're starting pretty simply, but still it's new. So what you need is one of the power supplies up there. You'll need alligator clip and a couple your multimeters. Wires will be hanging from the door. The right-hand door is probably best.